So to continue, in task 2, we generate a trajectory for each joint that moves from these to these values as shown here. And we plotted this using this code, where we used the method of cubic polynomials. We had 4 parameters that were computed using the theoretical materials we learned during the lecture. And then through these functions, we generated the trajectory using the given initial final joint angles. Okay, in task 3, we had to implement the function of inverse kinematrix's orientation. Basically, we were given joint angles. We had to find joint angles given the desired end effector's position and orientation. We did it by using the method of algebraic equations. To find these inverse kinematrix equations, we found them using the final transformation matrix and equating them with desired positions and the phi angle, and then we first solved for theta 2, theta 1, then, and the theta 3 was just a sum of angles minus 0, 1, theta 1, theta 2. Now, for the code itself, we had our original workspace in Cartesian space, and the user had to click to one point inside the workspace, and then the program will calculate the joint angles using this code, where we first gave link length and had the functions to publish angles and to deliver this inverse kinematrix with orientation function. Okay, where we basically replicated our codes, and then of course if user touch the area besides the workspace, it will give the outcome of target is out of reach. In task 4, we had to do, okay, so this is explanation, and this is how our real robot moved. So if we go here, this is how it moves. We start and it moves to a random point that user clicked and generated. Now in task 4, we had to implement a function to visualize the configuration of a 3-degree robot. That was the initial configuration. And then the final configuration using this code that's called 4.2. Task 4 used the previous mass considerations and generated the trajectory of the robot in the joint space. As you can see, this is the graph, so basically it had a little bit of a curved trajectory that started at this point, at the red point, and ended at the green point. Okay, so that's the code for this. We had to loop through this and generate it using cubic polynomials again. Now in task 5, we had to implement the same thing as task 3, but with via points. So here we chose 5 via points that we calculated based on the start and the end position. We chose 5 to ensure that it will move smoothly. So at the beginning you can see it's 45 degrees, and then it goes on to become vertical and reach the end position. Here how it looks. It first begins at the starting position and then goes through the via points, and at the end it will give us trajectory complete this program. We also simulated that in Gazebo. You can see it did the same motion there, and task 3 was also simulated in Gazebo. So in this one, yeah, we had to use our previous calculations of inverse kinematics and cubic polynomial, and also function of plot via points trajectory. We gave it a set of via points, initial final time, and the boundary conditions for position, velocity, acceleration. Now, where is the code? Okay, here is the code. And we of course gave zeros to joint 2 and 4 to ensure that it implicates these 3 degrees of freedom robot. So, and we use 2 loops here to generate the trajectory. Then we publish these angles to the 5 joints. When we did gazebo simulation, we had to change this publishing topics to these ones: robot, joint 1, position controller, and so on. So that's, and here's the photos. That's basically it.